if you're in my AP Calculus class, here's a little bit more for you. Okay, so gravity part 3. Where's the fastest part of an orbit? Well, I want you guys to think about something. Okay? So as you go around, here's the sun here, here's the Earth here. The Earth goes and makes some kind of a path. And actually, we're really close in. We're a very close, planet. We're the third one out, right? So we actually have a very nearly, almost perfectly circular orbit. As you get farther out, you get more of this elliptical thing happening here. But let's just think about this. In fact, let's just change it from Earth. Let's go ahead and say this is Pluto. Why not? Okay, we got Pluto out here, or a comet out here, instead of the Earth. Okay, so it has a really highly elliptical orbit, right? More squashed and uneven. So think about this. You're a farther distance away here. Okay, so out here, your radial distance from the sun, let's call it capital R. But some other point, you're over here, right? And you're only maybe small r away. Where are you going fastest? It's a good question, isn't it? So think about this. Where are you closest to the sun? If you could hit escape velocity, you'd be out at infinity, and your potential energy would be 0. Okay, we're closer in, so our potential energy is actually negative. Okay, but what we actually care about is total energy, is some number, because you're actually in a bound orbit. You actually do have some kind of number of energy there, right? Okay, so your kinetic energy and your potential energy make up your total energy. And remember, we actually had a negative potential energy anytime we're in a bound orbit, okay? Because we're going to consider potential energy, not R. R is not a P or an E. Okay, potential energy is equal to 0 at infinity, okay? Way out there. Pluto, not infinity. It's actually bound to the sun, which is why it orbits, okay? Or, slightly elliptically, more than slightly elliptically, but still. So here's the thing. If your potential energy out here, it's got to be a much smaller value, right? Let me think about this. You get closer and closer to 0 out here, but it becomes more positive as you go out this way, right? So your makeup of these two things, right, to get to that number, as your potential energy grows, right, you're going to get more of your energy stored as potential as you get farther out here, because it is a more positive value, okay? As you come back in this way, though, you're burning that up. You get a higher and higher negative value. So potential energy over radial distance away from the sun, going towards infinity out here, which we never make it to, right? But if you did, your potential energy would go up and not ever really quite touch, because gravity works forever, okay? But we can kind of fake it, right? Far enough away that you basically don't ever feel anything from Earth or the sun or whatever anymore. That would be infinity, okay? So as you go that way, farther out, your potential energy gets to be a higher and higher and higher, more positive value, even though it's negative overall still, right? It becomes more positive as you go out that way. As you go this way, it becomes more negative, right? So as you come in this way, you're actually losing potential energy and gaining kinetic. So as you come in this way, your kinetic energy goes through the roof. Kinetic energy goes way up, which means you've burned some of that potential. You've lost that, right? Your difference between here and here, potential energy for anything is always going to be mass of that object, smaller object, mass of the larger object, gravitational constant, and the distance between the two, right? So change in potential energy as you go from here to there would be, out here would be more, so you get mg over r. And as you come in here, it would be much less. It would be capital M, big G over little r. And the difference between those two would have to be your kinetic energy that you then have at that point. So your velocity becomes much, much, much higher here than it is out here. Okay? Farther you get away, it's like this. If I throw it up into the air, it comes and it goes slower and slower and slower and slower and slower and slower. It goes to a stop, and then it gets pulled back down slowly, 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 and faster and faster and faster and faster. Same thing's happening here. This is actually still just a ball toss up into the air, except for that's up into the air. So when I throw my pen up like this, that's Pluto trying to get away from the sun and then not quite being able to and coming back. And as it comes in here, you get a maximum velocity. Okay? Closest you are to the sun, your perigee, peri meaning near, right? Perigee is maximum velocity. Apogee, farthest away, equals minimum velocity. Farther you are away from the sun, slower you're going. That's it.